Welcome to the session Side-Channel Analysis Power. The first talk is called Generalized Power Attacks Against Crypto Hardware Using Long-Range Deep Learning. The work is done by Eli Burstein, Luca Invernizzi, Karel Kral, Daniel Morghini, Jean-Michel Pico, and Marina Zhang. And the speakers will be Jean-Michel and Karel.
Thank you. Thank you for coming also to our talk. We will try to make a good use of your caffeinated break. If you want to follow along, the slides are on the CHES website. You can also scan the QR code here to get access to them. And if you don't trust our QR code, you can also type the blue URL that is there. So I don't think I'm leaking any secret by saying that side-channel attacks are human labor intensive. You need to pre-process the trace, you need to analyze them, find point of interest, and then build your attack. So if you start considering the cross product of all the hardware that you want to run on and analyze the security of all the crypto algorithm and implementation and all the masking procedure that you want to deploy, then the cost will be prohibitively expensive and it will skyrocket. So our moonshot for our project was to leverage the recent advance in machine learning so that we can leverage deep learning, create a fully generalized automated side-channel attacks. And the skepticism might start building up. Why generalizing? Well, from our point of view, it brings four main advantages. The first one, we can process the full trace without human intervention. So it will automatically analyze the trace, find the leakage, exploit it. The model should work across the multiple algorithm. We don't want to have to change our model between AES, ECC, PQC for the next generation of algorithm. Similarly, for the countermeasure, we don't want also to update the model. We design the model once and it should work everywhere. And as I mentioned, it should be fully automated so that it can run in the background while you're busy doing more stuff. And the skepticism is probably going higher and higher. It's like fully automated, general AI ready. Well, these are the results we had. So we created an ECC dataset running on hardware accelerated and constant time multiplication in the hardware. Our model reached 100% accuracy in predicting the first attack point. The other are also in the same area, in the same range of results. Then we started putting masking on top of that. The traces were getting higher and higher. We bumped that almost to 18 million points for the trace, and the model was still able to catch up with that. Finally, we wanted to generalize, so we had to test on AES. So we were using the well-known and well-tested ASCAD V2 dataset against that. And again, our model was able to automatically find leakage and exploit it to find a key. So we're pretty comfortable that regardless of the algorithm, the implementation, the protection, and also the trace length, our model GPAM is able to reliably and automatically attack it. And that's it. That's all we have to say. No, just kidding. Of course, you want more details. So Karel will go into details about how GPAM model architecture works, how we designed it. Then he will go through the dataset that we generated and also that we are publishing on Google Cloud, so everyone can use them. Also with the dataset that were already published and that we used as part of the evaluation of our model. And finally, go into deep details into the results.
Thank you. So the GPAM model. Well, we combine, oh, thank you. We combine state-of-the-art techniques, and please note the plural, multiple techniques. And it seems to be providing a very general and efficient model that can be automatically tuned. Moreover, you do not need a big data center for doing this ML stuff. We worked very hard for it to be usable and trainable on commodity hardware. Think of high-end, but still gaming PC. And attacking a new implementation requires very moderate time. Here we are providing a guess of 700 GPU hours, which was consistent with the data sets we trained on. Obviously, if you have much larger traces, the results might vary, but yeah. How do we keep those promises? Well, our architecture, we feed the whole trace in, and we get prediction of 1 or more byte values. How does it work? Well, there are 3 phases to the neural network. First is a temporal stem, attention trunk, and multi-output circuit. And please note, I will be using heads in place of outputs. I will come back to that later. But first, for the temporal stem. From the trace length you have heard, the traces are pretty long. That's why we first chop them into chunks called patches, and then we project them to make them much more usable for the next phase. The next phase is using transformer layers. Why? Because the leakage might be hidden or scattered in the trace, and there might be long-range dependencies. And you might have heard that transformers are extremely good at picking up long-range dependencies. That's why they are used in many state-of-the-art models, such as ChatGPT or Gemini. Well, specifically, we use the gated attention unit 3 times with residual connections with compression block, which you may or may not use to further reduce the dimension. Finally, we feed this preprocessed information into the multi-output circuit. In our work, our main focus is on the evaluators, meaning white box. We know about the countermeasures. We know the values of random masks. Please note, during profiling, and during profiling only. What we observe is totally consistent with the rest of the literature. Multi-output works. Moreover, we notice that in some cases, if you feed predictions of intermediate heads into the secret head, you can get a boost in accuracy. So that's why there is configuration-based directed acyclic graph where you can inject your knowledge of the used countermeasure. Well, and now I have to apologize. This slide is for the ML enthusiasts. So just one slide. And yeah, if you don't feel like it and you heard a lot of ML, I will not be offended if you choose to check your email, but please come back later. So I was already talking about large trace and patchification, which is heavily inspired by image processing, right? The temporal aspect is we cut the trace into pieces which are collocated in time. And further, we have a learnable vector representation, which is similar to language models and so on. Yeah, for the second part, I was being a little bit imprecise. I was using gated attention unit and transformer layer a little interchangeably, which is not so precise, but I hope you will forgive me. Gated attention unit is very fast and provides same level of quality. That's why it's coming from the paper Transformer Quality in Linear Time. What's important both for gated attention unit and transformer is using of the relative positional encoding, because these layers need to know from which place the piece of information is coming. In our experiments, the rotary position unit seems very good, and it's a standard also elsewhere. And finally, with transformers, the weight initialization, like the random weights at the beginning of training, sometimes matter, and sometimes one can see differences in how the model converges or if the model converges. That's why we used Adam optimizer with carefully learning rate schedule, pretty much starting to learning quicker and quicker, and then learning slower and slower the nuances. Or one can use ADA factor as well. Okay. For the not so ML enthusiastic people, I hope you had time to check your email. And now for the data sets. Well, as Jean-Michel already said, we are evaluating both on state-of-the-art AES datasets and adding new ECC datasets. So what were the existing AES datasets? We evaluated on ASCAT v2, both SMASH and ASCAT v1. And yeah, there is also the AreaSure ECC dataset, which would deserve a slide on its own. And I'm sorry I put it into AES datasets, but it was feeling a little bit lonely. That's why we are creating 4 new datasets, which we hope will be of independent interest. We target the K82F, namely the LTC crypto accelerator, which has constant time multiplication and addition operations. To capture, we use LeCroy because of its high quality ADC and low noise level. And if you are super attentive, you can see that there is a label on the target board saying validation. That's because we are capturing the profiling data on one chip, train, and evaluating how the model generalizes on, well, different chip labeled validation. I was talking about 4 data sets, 1 chip, 1 capture setup. So first, we are using the unprotected, still hardware accelerated constant time. So I should say unmasked scalar multiplication. Okay, then we edit complexity by adding masking more and more. First additive masking, then multiplicative masking, and finally combining those 2. Please notice that the random masks are relatively long. Okay, this results in relatively large data sets, both in trace length and disk usage. So be careful, do not download them on your laptop, or do. And what are the results? Well, we focus on white box, as I was saying, meaning for the countermeasures, during training time, we have access to both the trace, the multiplier, and the random mask. During evaluation, the neural network gets the trace and that's it. It still predicts the multiplier, the random masks, but we just focus on the multiplier and ignore the random mask predictions. Moreover, what you can see is in the first line, in the not masked, I don't want to say unprotected, even models which were not specifically designed for ECC perform relatively well. But they do not perform that well, or I couldn't make them perform well on the masked implementations. Just noting the % is accuracy of value prediction of the most significant byte of the multiplier. Yeah. What's interesting, the previous layer we were using in place of gated attention unit was the convnext layer. Not the convnext architecture, which was originally for images, but convnext layer, a convolution layer. And it still provides pretty good results, but with the countermeasures, it fades. And gated attention unit seems to be working pretty well. The elephant in the room is these are accuracies, meaning can they be used for an attack? Turns out, yes. Turns out if you target the nonce multiplication in ECDSA, you can recover secret key using this information. Well, that was white box. We tried black box as well. Black box meaning during training, we had access only to the trace and scalar multiplier, not the random masks, which obviously does not matter for the first data set. But curiously, in the multiplicative masking, we still see leakage. We might have some intuition why, but that's still work in progress. Okay, so that would be for ECC. How about AES? Well, we tried state of the art. We totally admit we are not always top of the leaderboard, but the trade-off here is that all of the work was very much automated and done for us. And still, in each of the data sets, we see significant leakage, as in statistically significant. So we believe it would be a trade-off an evaluator might make. Okay, so what are the takeaways? We have shown that the model works with very little tweaks both on AES and ECC, and thus allows more automated training. The future work for us is obviously scaling up, benchmarking more algorithms, more implementations, more data sets. And the moonshot is being able to automatically pinpoint the leakage origin in the trace using explainability techniques in machine learning. Well, with that, thank you very much for your attention. If you want to get a paper, model, data sets, try them on your own, please follow the link, and I hope we have time for questions.
Thank you very much for the very interesting presentation. And we have quite some time for questions, so okay, maybe they're the easiest to do.
Thank you for the presentation. I have just a couple of questions regarding the assumptions you made. We didn't see any signal. Okay, everyone knows about the SCA. Does your method with the transformers resist all-time jittering and this sort of effects according to the cuts and the chunks decomposition you made of the initial signal? Unfortunately, we don't see any signal with deep learning. That's a pity too.
Very good question. I would say the ECC datasets have a very good trigger, especially with all the masking, there are multiple scalar multiplications. Especially the first one is very well aligned. The other ones, well, we used a control script written in Python, which might insert a little bit of a jitter, but not so much. We haven't gone for jittering in time specifically, no. I have seen some traces where we forgot where the trigger was, and it was still working, but much worse. There are obviously techniques how to train a model to deal with jitter. We haven't tried that yet.
And my second question was about the very strong hypothesis you make at the very beginning, is about the knowledge of the random during the learning phase. What's the meaning of it?
The meaning is because our work was primarily focused for implementers, where in the design of the when you're testing that on the FPGA or in simulation, you could leak this kind of information for training. The overall goal, as Carol mentioned, the moonshot, is to have an automated pipeline where you throw the data to the model, it spots the leakage, and then with explainability, it can goes back to you saying, no, you still have leakage around here, try to fix that part of the implementation. So that's why we took first the assumption, the heavily relaxed assumption, I agree, that the mask would be none. But as you saw, we also were able to attack CM2, so the multiplicative masking, even without feeding the mask to the model.
Okay. Thank you very much.
Hi, thank you for your presentation and this really interesting work. My question is about your the sampling rate you use. You said it's 50 megasamples per second. I think you use a pretty nice liquid oscilloscope. And also you mentioned that the tool can manage some traces with some millions of traces. So where could we go like, because sometimes we sample traces with a really higher sampling rate, and we get some traces like hundreds of millions of samples. Would it fit in your tool?
So the amount of samples should not be a problem to fit to the model. It's like the amount of traces of examples. For the traces, we haven't tested yet the limit. At the moment, for just the scalability of the capture pipeline, we're focusing on power traces because that's a more compact setup. But we plan to expand that to EM, where the traces and the sampling rate will be much higher.
Okay.
But we're pretty confident that the patchification should hold up, because again, the trace is just chunked. So you just feed the patches, it should work. Okay. But that's an ongoing work that we have. We'll try EM next.
Thanks.
Okay, please, we still have time for one more question.
Is there any desynchronization within SCA database or not?
No, I think we were focusing mainly the synchronized data set.
Okay. Okay, thanks.
Thank you.
Okay, maybe one more fast question. So just for me, fast, did you consider, so I've seen there the scalar masking, did you also implement any other point blinding or no? So that was not protected. Okay, thank you very much for the nice presentation once more. And now there will be the second talk, Tale of Snakes and Horses, Amplifying Correlation Power Analysis on Quadratic Maps. It will be given by Anna Guinet, and the work is together with Georg Land, Ion Gabriel Bukur, and Tim Gunesu.
Thank you very much for the introduction. I'm delighted to present this talk on behalf of my co-author from the Netherlands and Germany. Yes. In this presentation, we will make very simple assumption, and we will target a permutation-based algorithm with some quadratic function as an S-box. And from there, we try to see if we can use fewer power traces and reduce the computational complexity of an attack in order to recover multiple secret bits. For that, I will briefly introduce correlation power analysis, or more side channel in general, then permutation-based algorithm. Then I will present our optimization, which is combined CPA, or its nickname, a snake attack, and then show a practical evaluation on an FPGA. First, we assume we have a device with some symmetric cryptographic algorithm in it, which takes some secret input that has been stored in the device and some external input, here messages. The physical behavior of the device, meaning its power consumption, will vary according to the inner operation and data being processed. And we can use some statistical analysis on the measured power consumption in order to recover some information about the secret through the mean here of correlation power analysis. To do that, we have here on the left, our device with the secret key K. We input some messages and we will collect the power traces per message. However, those power traces are hard to explain. So to do that, we will take, on the other side, you have the cryptographic algorithm that has been implemented in the device. We take the messages, make some hypothesis on the key. Then through a leakage model, we will try to explain the power consumption of the device. And then we have a distinguisher, and we will see if we find a correlation between what we've measured and what we've modeled. If the model is accurate enough, and if our key hypothesis is right, then we will observe a high correlation. I'm sorry. Oh, yes. For our permutation-based algorithm, so basically it's an iterative application of a permutation F, here in a sponge construction. It works in two phases. First, the absorbing phase, which take here a key that is fully stored in a register, to which we will add a message. And then there is a squeezing phase that provides the output. For the sake of simplicity, in our attack, we focused on the first permutation here in blue of the absorbing phase. If we zoom in, we see that the permutation is composed of several rounds. Again, for simplicity, we focused on the first round of the first permutation. A round is composed of two layers, a linear layer, which is the composition of several linear mappings, and a nonlinear layer, which consists of S boxes in parallel. Here we choose to consider the remapping that is used in Ketchak-P on 5 bits and on for Xudo on 3 bits. And those permutations are used in various cryptographic algorithms. For the hardware, well, again, for simplicity and naturally, we consider here a register on which the round logic will be applied, and then the result will be updated, but again, back into the register. The message aim is only added at the beginning before the first round and not afterwards. For attack, for leakage model, we assume that there is no power consumption coming from the round logic, and we exploit the leakage of the register, and we assume as well that there is noise coming from elsewhere in the device. So if we stretch it a little bit more, here, the first one of the first permutation, we have the register state at time t0, which contains the entire bit of the key. We name the first n bits of this register state k prime. Then we have the message m. It goes through the linear layer, and then each n blocks will go through each of the S boxes and will be then updated to the register again. For our attack, well, actually, we focused on the first n bit after the first round of the first permutation here in blue. We will additionally use some extra intermediate variable. So here in the middle, we see lambda applied on m prime and k prime, which are the first n bits of k and m. Because it's linear, we can do this. And then lambda of m prime will be mu, and lambda of k prime will be kappa, the curly k. So I recall, for Xudo, it's n equals 3. For Ketchak-P, n's equal 5. All right. Then, our leakage model. So we consider things very, very simple. We only consider whether we have a bit flip or not bit flip. So the Hamming distance model, here we create a little function we call 1 if there is a bit flip and 0 if there is no bit flip. Since we focused on n bits, well, we sum them together, the function together, by putting this little, what we call activity function or oracle, I think in CPA, we put it to the exponent of -1. That meaning if you look at only 1 bit, for a bit flip, we have -1, for not bit flip, we have +1. So doing so, we just have a balanced model that is easy to work with. Let's go back to our attack and let's set it up. Here in red is what the adversary doesn't know. So of course, the value of the key and what is being stored in the register state, obviously at T0, but also at T1. Because the adversary doesn't know about the keys, they also don't know about kappa. However, they have control over the message M, therefore they know the mu. And they can measure the power consumption between the two registers, time T0 and T1. And as I say, we focus on the first n bits here in blue, so the output of the Ri on mu plus kappa. And the gray, we all say that it contributes to the overall noise. For our leakage model, so actually we can define the little activity function, the bit flip here, according to the algebraic, with an algebraic expression. So it's the first bit of the key that was stored, plus the first bit of Ri on mu plus kappa. Sorry, here it is expressed for the first bit of, the very first bit after the first one. So you see, it depends on 4 unknown bits and 3 known ones. We then relate that to the power consumption. So again, very simple things with an additive model where we have a signal part, which is the contribution of those n bits of the noise, plus of the signal, the n bits that we target, plus some noise, which is just a Gaussian with a 0 mean. So for the signal, it's easy to differentiate whether we have bit flip or not here for 1 bit, and here we have a Gaussian. For the noise, if we add them together, we see it's a little bit more difficult to distinguish between the two cases. So in order to exploit this, we will partition the power traces by inputting many messages. The adversary will retrieve the power consumption, so they only know about the P, of course, obviously not about the different elements of the S and the R. And normally in CPS, they will partition it in 2 categories, so the bit flip and not bit flip. However, when we look at the algebraic expression of the activity for the power consumption, we see it depends on 3 bits of the message. So we find it more efficient to exploit this information and partition it according to the different values of mu's. Therefore, we can collect our traces and take the average of each partition. So here, with a few bits, we have a lot of noise, but if we take many traces, of course, we can reduce the influence of the noise and differentiate between the different cases. Let's go a bit over that into detail. So I recall the activity function for the very first bit. So naturally also, we will go over all the different, all possible inputs for this function and build these tables, the signal, what we call signal power consumption values of reference. So here in the rows, you see the values for the different messages, and in the column for the secret. We consider the sum of k prime 0 and kappa 0 all together because you see it's simply added in the activity function. And then we will take the Pearson correlation coefficient between our power traces and each column of this table. And then we will take the highest correlation result as our most likely guess. However, here is an optimization coming on. If we look at the last 4 columns here in blue, we see that they are exactly like the first 4 columns in white, except that the sign is flipped. It is due to the sum of K prime 0 and kappa 0. So actually, they don't contribute so much. We can discard them. And therefore, we only consider here kappa 1 and kappa 2. And for doing that, we take the Pearson correlation coefficient, we square it, or we take the absolute value to discard the sign. We observe that the same thing is happening here on the last 4 rows in blue for the mu's. And actually, the most relevant information is here in green. However, for sake of simplicity, I mean, it's just easier in practice if we just keep the column as it is and without changing the mu's, but it is possible to go further. So we have seen, that for 1 bit of, we're targeting 1 bit, and then we can retrieve 2 bits of information. So let's do that many times. So we here consider n equals 5 bits, so we're targeting K-check P. If we look at the very first bit, we can recover kappa 1, kappa 2. Then second bit, kappa 2, kappa 3, kappa 3, kappa 4, kappa 4, kappa 0, kappa 0, kappa 1. Great. Now, if we combine them in a coherent manner, we can recover the full kappas for the 5 bits. So by summing the individual results. And here you see there is this nice little, looks like a snake by combining the results, hence the nickname of the attack, the snake attack. So here we have for each bit, we had 4 results that we combine, well, 5 times. And this helped to reduce the computational complexity of our attack, because in more traditional CPA, we will have to target the 5 bit of kappa prime and the 5 bit of kappa at a time. And this works because we exploit the redundancy because of the he function, we exploit the redundancy of the information. From there, you can recover kappa prime simply by afterwards, once you have recovered the kappas, you can exploit the sign of the Pearson correlation coefficient to recover the secret that has been initially encoded in the register. So here an example for K-check P. So we successfully reduce the computational complexity. Here's some practical evaluation on an FPGA. This is an example for Xudu. So we look on 3 bits. We see we have first on the left, we have CPA. So we recover, so with this attack, you recover kappa prime and kappa all at once. But with combined CPA here, we just recover kappa, and then afterwards we recover kappa prime. And we did that by squaring the correlation coefficient. We saw in practice that either squaring or taking the absolute results just provide the same. There is no advantage using one more the other. So here what we have in each graph is some plot lines for the secret to be guessed first, second, third, fourth, etc. Different rank. And the line that goes all the way to the top, to the success probability of being 1, is for the secret to be ranked first. And we see that after, with the number of power traces, the secret to be ranked second, third, fourth, well, will go back to probability 0. And with our snake attack, we need fewer power traces in order to reach the probability of success of being almost. So actually here it's almost 1. This is snake approved. Where does the horses come into play? Well, at a given number of power traces, you see that we have all those different, like we have the probability of success to be 1, 2, 3, 4 for the correct guess. And if we add them all together, those probability equals 1, and they follow a particular order. And this is what has been described by the Henry model, usually designed for horse racing. So this is where it comes from. In his paper, he explained it for Gaussian probability distribution. Here, it's for Pearson correlation coefficient results. This is, in his paper for Gaussian, it was actually not so trivial. And here, it is actually rather difficult to model it. So we rely on experimental data. We can see that the same result, well, we can have the same conclusion coming for Ketchak P, so focusing on 5 bits, n equals 5. So we as well need a fewer amount of power traces in order for our secret key to be ranked first, here higher than for traditional CPA. Also, the starting probability, forgot to mention, is slightly higher for snake attack because we consider less intermediate results. So this is as well snake approved, and it does follow the horse, the NRE model for horse racing. Now let's look at the probability of not having the secret key being rank 1. In the plain line, it is the result for the snake attack, and in the dotted line, it is for traditional CPA. We see that for the snake attack, we have a lower probability to not having the key as being the best guess, which is actually so what we want. We're really happy about this because it means that the snake attack is performing better. In conclusion, we successfully could, with very, very simple assumption in a very simple setting as well, we could leverage the algebraic expression of the S-box in order to reduce the amount of intermediate result to manipulate in order to have a higher probability of success than like a traditional CPA for the same amount of power traces. Thank you very much for your attention. We have the artifact as well available. Thank you.
Thank you very much for a great presentation. Are there any questions? Okay, maybe, okay, then. Yeah, here's the easiest.
You stated that you evaluated the Henry model for multi-entry order rank competitions. Have you evaluated the extended other entry models and seen how good their fit is for your data sets?
Oh, no, sorry, not in that way.
Okay.
So we had, when we look at those results, let me go back to this. Well, we had this experimental data, and we see at a given number of power traces, we have this different probability of success. You look at they look rather nice, and they all sum equals to 1, and they follow a particular order. And we were like, there must be a model to explain this. And then we talk and look up there and try to find a way to model this. And it actually one of my co-authors was like, oh, there is this paper about horse racing. It seems to fit. And so we just explaining about it, and then we try to find more, to write the result, find the variance experience, like really write it down, and it actually not so trivial. Okay. So in the paper, he does it for Gaussian probability of success, and it's already a bit laborious. So, I mean, more work is needed here, but we want to just explain it through an existing model.
Okay, so you haven't looked at non-Gaussian distributions then?
I think here it's not Gaussian, but it could be further exploited, investigated, yes.
Okay, are there any more questions? Okay, I do have one question. So your evaluation was done on FPGA?
Yes.
Would you expect the attack to work with the assumption similarly well on against the software implementation?
Oh, we haven't considered this. I think the attack is mainly coming from theory by looking at the key function. I'm no way less about software, so I don't really want to advance too much, but yeah, I will ask my co-author, we know more about practicalities to answer on that.
Okay.
But it was really made from just looking at the algebraic expression. So,
no.
yeah.
Okay, that's clear. Thank you. Thank you very much. So thank you once more.
Thank you.
Okay, and now we will have the third presentation, and not so discrete sampler, power analysis attacks on Hawk signature scheme. The talk will be given by Morgan Guerreau, and the work is together with Melissa Rossi.
Hello, thank you for attending my talk. This is a joint work with Melissa Rossi, which is called Not a Discrete Sampler, Power Analysis Attacks on Hawk. So the Hawk signature scheme is a lattice-based signature scheme that has been submitted to the second NIST call for a post-quantum signature scheme that was issued last year. It shares a lot of similarities with Falcon while being another lattice problem. And so the question arose, does it also share the same side channel vulnerabilities? Because in the past few years, there has been some attacks specifically targeting the Gaussian sampler of Falcon. And the answer is yes. So today we present the first power analysis attacks on Hawk. First, a few words about lattice-based cryptography. For those who are not familiar with it, it is usually a common problem that is used to build lattice-based cryptography is the closest vector problem called CVP. Given a lattice lambda and a vector C in Rn, you have to find a vector V in the lattice lambda such that the distance between V and C is minimal. CVP is easy to solve with a good basis, but it is hard to solve with a bad basis. And a basic signature scheme would be to first convert the message to sign to a vector C in Rn. Then you would use a good basis, which would be the private key to solve CVP. And finally, anyone would be able to verify the signature V with a bad basis, which would be the public key. And of course, it is hard to derive the good basis from the bad basis. Otherwise, the scheme will not be sound. But in today's lattice-based cryptography, you do not find a direct solution to CVP because it leaks information about the private key. There was a few attacks in the past about that. So the solution is to use the so-called GPV framework and to return a not always closest vector. So you won't be returning the closest vector, but you will return a vector that is close enough to your target. And for that, you will need to trap the sampler. And the trap the sampler will be the target of our attack. That's the reason I'm boring you with all of this theoretical stuff. Now let's have a deeper look into the Hawk signature scheme. As I just said earlier, it is an association of the GPV framework. It uses entry lattices with a special case that the modulus Q will be 1. And so the private key will be very similar to Falcon and so on. You will have 4 small polynomials which will satisfy the entry equation. Your private basis will be only this matrix of the 4 small polynomial, and the public basis Q will be the product of the Hermitian adjoint of the private basis by the private basis itself. And very high-level overview of the signature procedure is as follows. First, you will sample a random salt because it's a hash and sign signature scheme. Then you will hash the message and the random salt to vector H. Then you will compute the target T by multiplying this vector H by the private basis B and taking the result mod 2. So we will have a binary vector T that you will feed as an input to your Gaussian sampler sample sign. And this sample sign function will return you a vector V, vector X, sorry. And finally, to compute the signatures, you are going to multiply this vector X with the inverse of the private basis B. And of course, you have a few things that happens later in the scheme, but W is a public value, so we can stop here for the sake of the presentation. Some Hawk particularities is that CVP is not solved in the lattice generated by the private key, solved in an isomorphic one because it's built on the lattice isomorphism problem, but we will not speak about that. But another particularity which is of particular interest for us is that the L2 norm of X is actually known because it is equal to the Q norm of W, and W is a public value. So this is not a vulnerability in itself, but this will help us in our key recovery later. Now let's have look at the Hawk Gaussian sampler. It's a table-based discrete sampler. It outputs a vector X from Gaussian distribution in the lattice coset translated by T, T being the binary vector, so either 0 or 1. And it has a fixed standard deviation sigma, which is a public parameter. So a very high-level overview of what such CDT sampler looks like is as follows. First, you are going to sample random value C, which for Hawk is of 78 bits long. And you are also going to sample a bit B. Then you are going to go through a reverse cumulative distribution table, and you are going to compare your random value C with every entry of the table. And if your value is lesser than the entry of the table, you are going to increment a counter R, such that in the end of the for loop, R will be equal to a value somewhere between 0 and 13, so, which is the length of the RCDT. Then, once you have gone through the whole RCDT, you will apply a parity to R, which here will be the value of your target T, and you will apply a sign, and so finally, you've done with your sampling. So now we are going to perform a power analysis attacks on Hawk. And here is a overview of the key recovery. First, we will perform the simple power analysis on the sample sign to recover partial information on the output X. And then we will either perform a smart brute force to recover the mixing Xi and then the private key with basic algebra, or we can also apply the leaky LW tool to recover the private key via lattice reduction. Let's have a closer look at sample sign code. So here is the C code from the reference implementation of Hawk, and I have highlighted the lines that will be of particular interest for us because they will leak a lot of information about the manipulated value. So first line is a sign computation. It will leak information because the value in the neg variable will have a Hamming weight, will be either 0 or 32 depending on the sign, so this will leak. Same thing for the parity on line 3. We will have a Hamming weight, which will be either 0 or 64, so it will leak even more. So that's some stuff that's happening at the beginning of the algorithm. And then you will have the actual comparison with the RCDT. So you are going to compare your random value, which is CC in the C code, with every entry of the RCDT table, and this will happen inside this for loop. And one interesting point is that in the Hawk sampler, you actually have 2 columns of your RCDT depending on the parity of T. So you are going to sample either from one column on from the other, depending of the value of T. And in this implementation, you will check the parity of T in every iteration of the for loop. So the parity of T will leak in every iteration of the for loop. So we will have a lot of leakage points to recover the parity. And also in pink, you will have the actual comparison between your random value and the entry of the table. And this will leak because the size of the register is greater than the size of the considered value. So you will have an underflow during the comparison, which will lead to greater Hamming weights in case of the result of the subtraction is negative. So here is the second part of the code. There is a second for loop because they split the RCDT into 2 parts, but it's basically the same idea. And after the second for loop, you will then apply the parity, so this will leak. You will apply the sign, so this will leak. And there is something that has to be done in the Hawk signature scheme, but not necessarily in the sampler, which is the computation of the norm. And the computation of the norm, since it is performed after the application of the sign, this will be also very leaky regarding of the sign of the sample, because if you multiply together 2 negative numbers, the Hamming weight will be much higher than if it is 2 positive integer. So here is the overview of a single execution of the sample sign. And you can see quite easily that we have those two for loops. The first for loops has 5 iterations and the second for loops has 8 iterations. And the peaks are quite visible, so you can quite easily separate and split your power traces to locate very precisely each iteration of the for loop. And this will help us because we can know quite precisely where we are in the code execution, and this will help us match the points leakage to the corresponding C code to understand what's going on the power traces. First of all, we are going to recover the sign of the sample. So the sign of the sample leaks at 3 different points. First, during the comparison of the sign, then during the application of the sign, and finally during the computation of the norm. It looks a little bit better on my computer, but know that the traces are online in the GitHub repository, so you can just plot again the picture and zoom as much as you want if you want to have a closer look on what it looks like. And as you can see, the power traces divide themselves into 2 groups, and it's quite visible with bare eyes. So we do not really need fancy machine learning. Any simple threshold on the average value will be enough to actually separate the 2 groups of traces. One interesting point is that is the special case of the zero. The zero coefficients, they get a sign that is drawn, a sign that is applied to them, even if eventually zero can be considered as positive integer, because even if the point of view of the Hamming weight, zero have Hamming weight of 0. So it's very close to, it should behave like a positive integer, but since it can have a negative sign that is drawn and applied to them at the beginning of the algorithm, it can behave like a negative integer and be classified and be wrongly classified as a negative integer in our first analysis. But since we are able to identify them as a positive integer in the last operation, which is the computation of the norm, we can take the intersection of those 2 classifications to identify half of the 0, which amounts to around 7% of the coefficient, which is not that much, but it's nice anyway. Now that we have the sign, we are going to recover the parity, so we have something quite similar. Here I plotted what I talked about a few minutes earlier, is that you are going to choose between 2 columns of the RCDT during each iteration of the loop. So this will leak, you will have a multiple point of leakage for this leakage that I've shown on the screen. And also you will have a similar leakage to the sign for the application and the computation that I have not shown on the slide. And then finally, now that we have the sign and that we have the parity, we are going to recover some information about the actual value of the sample. The comparison is implemented as a subtraction because it's a constant time sampler. And so as a result of this subtraction, then R will be either incremented or not. One interesting point is that R is if R is not incremented at a certain iteration, it will not be in the following one. So we can use this to further refine our classification and discard false positives. I've plotted the comparison during the first iteration, and here you can split the power traces into 2 groups. For later iterations, the difference in power consumption will become less obvious, but it is still possible to exploit them without doing any prior profiling. In the end, we will not be able to recover everything, but what is important is that we will be, thanks to our methodology, we will be able to classify coefficient with no false positive. So if we are able to classify a coefficient, we can know for sure that it was correctly classified, and we can know for sure if a coefficient is, if we have no idea about the value of a coefficient, we can know that and we can just put it aside for the moment. So that's the results we got for HAWK 1024. We were able to retrieve almost all of the coefficient, and the only coefficient for a sample of 10,000 coefficient, the only missing coefficient were the 4 and the 6 coefficients. And so now I'm going to explain how do we recover the private key from those samples. So first, let's recall that we have W, which is a public value, equal to the inverse of B times X. So X is the sample that we are trying to recover elements of it, and B is a private basis. And so if we get two W and W prime linearly independent, we have the following equation that also with basic linear algebra, we can recover the private key, which consists in the four polynomial f and g. We also have the L2 norm of x, which is known. So we can rewritten this expression by subtracting the non-coefficient that we recovered in the power analysis just before as follows. And since we are only missing coefficient whose value are either 4 or 6, we can still simplify this equation as follows. And this equation has a very low complexity for exhaustive search because it's bounded by a binomial coefficient. And in the end, we only have 2 to the power of 36 possible combination, which is not that much. Also, in the event that we had recovered less xi, if we have less information of the sample x, because maybe we are in a more noisy setup or other explanation, instead of brute forcing the remaining coefficient, which could be very resource consuming, we can use lattice reduction. Let's have a closer look of x0. X0 is the first half of the sample x, and it provides linear information on the secret polynomials f and capital F. So we can use it with combination with a leaky LW tool on the lattice lambda t, which is generated by the transpose of the private basis B. And every different type of knowledge gain over X will be a different type of int in the leaky LW tool setup. If you gain some knowledge about the sign of X, it will be an inequality hint or approximate hint. If you gain some knowledge about the parity of X, then it can be considered as a modular hint. And if you get some knowledge on the value of X, then it will be considered as a perfect int that you can feed to the tool. So about the results, what is interesting is that, of course, you can combine the parity and the sign. But what is interesting is that the parity actually decreases more the security of the problem than the sign. So if you had to make a choice and protect only something in the sampler, you should go for the parity because it decreases the security more than the sign. And here we have the results for if you get the parity the sign, and then you get an increasing number of coefficient of x0. So you can see that it decreases, and you can estimate the residual complexity depending on all those parameters. So to conclude, so we presented the first side-channel attack on Hawk's miniature scheme, and this may be unsurprising because Hawk is actually not claiming any protection about side-channel attacks. But to our opinion, it highlights the needs for protection, as this is a non-profiled attack with very low resources. Additionally, you can see the paper for a template attack for full key recovery with no offline computation, and also for simple tricks to mitigate the leakage of value and parity. Future works could be to exploit more information on X with the leaky LW tool, because as I said earlier, we are only exploiting the first half of the sample X because the other half is providing information on other part of the secret polynomial, so it's not trivial to adapt. And of course, future road could be to provide a probable countermeasure for the Gaussian sampler, as we only provide simple tricks to mitigate the leakage. So thank you for attending, and I'd be happy to take any question.
Thank you very much. Are there any questions? Okay, then I have a question. So it's mentioned that the attack is non-profiled.
Yes.
I assume that's so if you would like to automatize it, because you were showing SPA, but I assume it would be like clustering or something like that, or
like what? Sorry.
The recognition. How did you automatize that recognition of values using clustering or?
Actually, I did not automatize. I found the point of interest by hand because by looking at the power traces, because you can see very easily when you are in the power traces, and then to separate the traces into the two groups. For the parity sign in the first iteration. I just computed a threshold, an average value for the traces, and then just split it into two groups depending of the threshold value.
Yeah.
And then for the following, I did more statistically evolved stuff, but basically not that much.
Okay, so okay, but that's like class setting, sort of just very simple one.
Yeah.
Okay, that's clear. And okay, for template attack, I will have a look in that paper.
Yeah.
So okay, thank you very much. Are there any more questions? Okay, in this case, thank you once more.